SGD, stochastic gradient descent. One of the coolest names of anything you'll ever do in artificial neural networks, although the name long short-term memory is kind of neat as well. But what is stochastic gradient descent? Gradient is a fancy word for the derivative. The same way that reactance is effective resistance when you're talking about a reactive element, a gradient is a derivative in a certain context. Let's say you have this function. This right here is called a minimum. It's where the function's value is at its lowest. And it doesn't have to be the only one. You can have a function that does this, and all of these are minima. Every single one of them, even this little one I accidentally drew, all of those are minima. But this is what's called the global minimum. Let's say that the function, let's just say it goes like and stabilizes. This is the absolute lowest value the function ever gets to. So that is the global minimum. All of these are local minima, but there's only one global minima unless there's, another one at the same spot. It's not useful or meaningful to worry about multiple global minima because we're trying to get to a minimum. Ideally, stochastic gradient descent is something that always finds a global minimum. It doesn't. And there's fancy stuff, the momentum and blah, blah, blah we'll get to in the future. There's advanced techniques to make it more likely that you find this one rather than any of the others. But if there's multiple at the lowest value, it doesn't matter. We just care about the lowest value. So stochastic gradient descent is a technique for getting to a minimum, hopefully the global one, but at least a local one. And that's what matters. Descent. Well, I mentioned gradient is the derivative. So let's say you're here. You're here. This is your x value. You want to get here. But let's say it's not a simple, function. We can see this. We can see this function. Obviously, well, there it is. But what if this is a function of 8,000 variables? What if this is an 8,000 dimensional function? You're not doing that algebra. Even a computer is not doing that algebra. You're going to be using approximation techniques to figure this out. You can't do the partial derivatives combined of 8,000 variables in a couple sheets of paper. This two-dimensional, well, one-dimensional, because there's only one input, the other one's the output. So this one-dimensional function, two-dimensional plot, just illustrates the idea. So assume that we want this derivative, and we can calculate this derivative, but we can't just calculate the minimum. The idea is we know that wherever we are, the minimum is down. This is why it's called gradient descent. We take the gradient and we descend. We're going downhill. The analogy is going downhill, so we start here and we go a little bit. We don't want to go forever because we'll end up down there. And this is where we get stochastic. Stochastic is a funny word. I actually always forget the formal definition, but in this case, it's basically just a piece at a time. We go a little bit. We go like this. We go a little bit, little bit, little bit, little bit, little bit. Whoops, now we're going uphill. Stop. You basically go down the hill, down the hill, down the hill until you're going uphill. And then you say, I don't want to go uphill. I want to be down. So you just wiggle your way into a final value as precise as you want. So stochastic in this context is just referring to the idea that you're going a tiny bit at a time. Because if you calculate the gradient here, the derivative here, that's very different than down here. So if you calculate the value once and then just try and go for a while, you're going to blow right past it. You can't see. You're trying to do this for 8,000 variables. And computers can do that great. Computers can number crunch great, but they don't know how far to go. There's no formula for go this far. So you've got to go a little bit and then see the new gradient, and you want to watch the gradient. If the gradient is getting shallower and shallower, you go, hey, that's good. And you just keep going until the gradient is flat. And if it goes uphill, go backwards until it's flat. So this is stochastic gradient descent. You have a function of so many variables you can't do anything with it. You take the derivative, and then you go down a little bit. How much? You tweak it. Go a tiny bit at a time. If it's too slow, speed it up. Just increase how far you go. If your numbers are wild and oscillating, then you're probably, going too far and you're jumping here to here to here to here to here to here. Slow down and you'll start, slowing down and you'll get to this point you can go So that's something you have to manage manually when you're doing this. You kind of just watch it, or you could have a computer program to see if it's slowing down or not. But basically, you just go a little bit at a time and go down to the bottom. That's all it is. That is stochastic gradient descent. So why are we trying to get to a minimum? Ideally the global minimum, but any minimum will do. Why are we doing this? Because the function is an error function. In other words, we have this plot, 8,000 dimensional or whatever. But the plot is how wrong we are. Basically, if we're here and we calculate whatever we're calculating, we're wrong by this much. But if we're here and we calculate whatever we're calculating, we're only wrong by that much. We want to be less wrong. So why can't we just figure that out? Because it's 8,000 dimensional. Let's say we have a function. Its inputs are x and w. X is the actual values. This is the math we're trying to do. F of x, that's the thing we're calculating. In this case, x, you see that bar over it, it's a vector. X equals 2947. However many inputs. Just as many inputs as we want. The same for w. But w is something called the weights, or the parameters. If we have f of x, y, z equals a times x plus b times y plus c times z plus d. This is a three-dimensional, it's just a simple linear function in 3 dimensions, or a plot of 4 dimensions, so I guess it's a hyperplane? I forget what it's called, but anyway. The point is, we've got a, b, and c. If we do it this way, x bar equals x, y, z. That's our input. That's what we care about calculating. And w equals a, b, c, d. What's the point of this? The point of this is we're trying to find a function. We don't have a function and do math with it. We don't even have the function. We know how we want the function to work. We know the outputs we want it to give. But we don't know what a, b, c, and d are to give the right result. We know if x equals 1, y equals 2, z equals 3. We want this to be 9. We know that. For example, we could know an infinite number of results, but we don't know what a, b, c, and d should be to make that happen. And in this case, you probably could do some algebra to figure it out. It's just a linear function. But if you have 8,000, A, B, C, D, E, F, G, 8,000 of those, no. And this is where we use computers. Stochastic gradient descent is basically how you train AI in the simplest form. And there's more advanced forms, but SGD is the starting point because it's easy. What do you use for these weights? What you do is you just initialize it randomly. All this A, B, C, D, you just pick random values. A lot of times they'll pick it from a normal distribution, which I'll talk about later, but basically just pick random numbers, anything you want. And then you calculate it. You pick an input, 1, 2, 3, and you know that 1, 2, 3, if you put it in, should give you 9. But of course it's not going to because A, B, C, and D have been picked randomly. So you know that 1, 2, 3 should equal 9. You actually get, 94. So your error, there's different ways to calculate error, but there's a certain error. Between these two, you can mathematically express how wrong that is. So then you have, your error, and these are different values of A, B, C, and D. If the values of A, B, C, and D are here, you're very wrong. If the values of A, B, C, and D are there, then that's as good as you're going to get. It may not be exact, but it'll be close. We want to get as close as we can, minimize the error. So what we do is we get the derivative of weight with respect to the function. If we change the weight, how much does it change the function? Or in other words, how much does it change the error? So if I calculate 1, 2, 3 and get 94, and then I say, well, let me take C. Let me take one of these weights, and it might be 12. Let's make it 13. What if I change C from 12 to 13? Well, you have your error function. Let's say C12 is there, C13 is there. It's a gradient, so you can say, oh, if I change C from 12 to 13, I'm increasing the error. So maybe I'll change it to 11 instead. This is the purpose of stochastic gradient descent. It's when you have parameters to a function that are going to do math for you, and you can't calculate those directly. You instead pick random parameters, and you do some math, and you figure out how wrong it is. And then you figure out how you change those parameters to be less wrong. But you don't have just an instant result. You don't just calculate and say, oh, well, if I change the weights to this, then it's perfect. You have an 8,000 dimensional function here. And what you get is your gradient, your derivatives, that all tell you how to reduce the error. But you don't know how much, so you do a little bit. You say, okay, that's downhill. Let me go downhill 1 inch, and then calculate the new slope of the hill. Because you're completely blind here. You don't know, you know what the slope is, but you can't see the hill. That's the thing. If you want a physical analogy, you're going downhill, but you don't know which way down is. You don't have gravity, you don't have, your balance, you have nothing to go by. All you know is this is a slope. You can for whatever reason, you know that the spot you're standing on downhill is that way. You can't see the hill behind you, in front of you, anywhere. You can't see anything. All you know is the spot you're standing, that's downhill. So you take one step, and then you say, okay, downhill is now this way, and take one step. Now downhill is this way. You take one step, and you hit your foot on a printer. That's what stochastic gradient descent is. Normally, we think of a function as just inputs and math, and you get an output. But in this case, you don't know the math. You know how you want your AI to behave. You know if it is standing up or falling down. You want it to stand up, so every time it falls down, it's an error. And you say, that's wrong. You shouldn't be on the floor. You should be like this. So then you calculate what caused that. We'll get into that in AI. But you have an error, and you want to reduce the error. Whatever math it used, it raised all four of its legs at once, and then it fell. Whatever math caused it to do that, you say, no, that's bad. So you reduce the math that made it lift all its legs, and next time it only lifts one leg, or whatever. Because you don't have this function to just say, okay, well, you can't just tell it, well, don't do that. We have to do fancy math. That is what stochastic gradient descent is. People complain that I go over the same thing multiple times and I get boring because I say it 4 times in different words. Welcome to this channel. If you can read a 3-page tutorial in 4 minutes and understand AI, go do that. You're here because you're a bus driver like me who needs a little extra going over it to get it. Or you just like beards. So whichever it is, I'll be seeing you.